Hello, friend. My name is Derek Harder, and in this video, we're continuing to talk about some of the fundamentals of machine learning, but with kind of respect to neural networks and deep learning models. So, in this video, we're going to be talking about improving the fit of your model. Okay, so in order to achieve the perfect fit, you have to first overfit, to get that balance. And since you don't know in advance where that boundary lies, you have to first get a model that can overfit. But you might not be able to get there right away. So there's three common problems. We're going to go through them kind of one by one and try and give you an intuitive feel for what we mean by those, and then some strategies you might take to overcome those. So the very first thing that could happen is training doesn't get started. So your training loss doesn't go down at all over time. It's kind of the easiest to overcome. But then you might have it that training gets started fine, but your model won't meaningfully generalize. Okay, you can't. Your validation data can't beat that general common sense baseline that we talked about in a previous video. Both of those aren't happening. You might have a model that seems to be training and validation loss is going down. And you beat your baseline and it's generalizing, but it doesn't seem to be able to overfit. Okay, so that indicates that you're still underfitting. So let's get started. Let's look at those three problems here. So the first of these, if your training doesn't get started or it stalls too early, or your loss is stuck, it's always kind of a problem with the configuration of gradient descent. Okay, so you might have to change your choice of optimizer, the distribution of initial weights, the it's usually sufficient to look at kind of the learning rate, and the batch size constant that you have. Okay, so an example of what that looks like can kind of clear up what we're talking about here, right? So here we'll go back and use our MNIST data that we've been using. So you should be familiar with, but we're going to choose an inappropriately high learning rate, right? So we'll set it to 1.0 here for our optimizer. Okay, so you'll see as this trains here, I'll go ahead and let this train, and we'll visualize the result of the training after we fit our model. So once the model finishes training, you'll see that it quickly reaches a validation and a training accuracy of 20 or 30%, which is a little bit above the 10% kind of baseline, but it's not very good. And even more, if you kind of look at the loss curve, you see the loss curve is not going down at all in the training data as you would expect. Okay, so it's not performing gradient descent. So to me, this is probably the most indicative of this kind of problem. The training loss is kind of pretty much flat after the first epoch or two, not doing much. Okay. So if you see that, like I said, maybe try playing around with your optimizer or your learning rate, or you can try changing your batch sizes. That can have an effect. So here's a more appropriate. So if we change the learning rate to 0.01, and go ahead and train the same model again on 50 epochs, let's let that train. So once training finishes, let's look at the learning curves again. So this looks much more reasonable, okay? So especially what I'm concentrating on here is looking at the training loss. So if you're not suffering this first problem here, where gradient doesn't, appear to be working. So here it appears to be working. So you should immediately see some rapid loss on the training data, and it probably should continue to kind of go down, even though in the first 10 or 20 epochs it's going much faster than it does here, right? Also, looking at the accuracy, I mean, both of these are doing much better than kind of a baseline of 10% that you'd be expecting here. So yeah, if gradient descent doesn't seem to be happening at all, try first looking at your optimizer. Lowering or increasing the learning rate can help. The batch size samples can have an effect on this. So the idea is that when you have larger samples, you reduce the noise in your update step. So it can be more informative if you increase your batch size that you're using when you're doing training. So for the next one here, you've got a model that fits. So it seems to be, gradient descent seems to be working, but for some reason your validation metrics aren't improving at all. So they kind of stay, they're not able to beat the, they're not able to beat like your baseline, like a random, the performance that a random classifier would be able to achieve. Okay, this is unfortunate. This could be an indication something's really wrong. This is kind of one of the worst situations you can find yourself in. So hopefully this isn't the case, but one possibility is that the input data you have just doesn't contain sufficient information to reliably make predictions. Okay, so if that's the case, so yeah, I mean, if it's this first case, there's really nothing you can do. The problem is formulated. The data as you have is not solvable, right? So of course, if you have to use that data, you're gonna have to assume that hopefully it's something else. It could be that the type of model you're using isn't really suited for this problem, right? So later on in this course, we're going to be looking at different kinds of architectures that work well for like image data or for sequence data, time series data, right? So if you have data sets that are kind of more in those areas, you probably, if you're trying to use a more basic architecture, have to use something that is known to work well with those more specific types of data sets that you might have. One thing we'll look at is hopefully if it's not the second case where you might potentially be in a pretty bad situation, not have data that you can actually model. So in this third case, your training and validation loss are both going down. So gradient descent is working, you can beat your baseline, so you seem to be generalizing. Your validation metrics are better than kind of what your random baseline or whatever baseline you picked, but you don't seem to be overfit. So you never see the case where the validation loss goes down, but then starts going up again. You haven't seemed to reach that point of overfitting, right? So that indicates that your model is still underfitting. So this is usually just a problem with the capacity of your model, right? So if you increase your model capacity, before you can start seriously tuning and finding that boundary, you need to have a model that is capable of overfitting. So you want to increase your capacity if it seems like gradient descent is working and it seems like you're able to generalize and beat your baseline, but you can't get it to overfit. So let's say we're using a simple logistic regression model. Okay, so this is equivalent to a simple logistic regression model because we're using a single layer in a network here, right? Where we give softmax activation. We're going to use the MNIST data again here. So softmax for 10 outputs. So in this case, the logistic regression isn't sufficient in order to do a good classification for the MNIST data set. So let's go ahead and let this fit here. So once it's done, if we look at the learning curve, we can get a better visualization of what we mean by that. Okay, so it seems to be doing something. We know that we should be able to reach like 99% or so on a good model, but even if you didn't know that, if you're working with a data set that's never been done before, the thing that we're kind of focusing in here on is the validation loss, right? So, it slows down and maybe even state kind of comes to a point where it's flat, but we never see that characteristic where it begins rising again, which is indicative of overfitting on the model, right? So, it seems to be beating the baseline. We're doing much better than 10-20% here, so it's doing something. It's not useless, but we haven't reached that that point of overfitting, so we can probably get much better of a model if we keep working on this. All right. So adding more representational power is always possible when you're working with neural networks and deep learning. You can add more layers, you can add more units to the layers you have. So instead of using a simple one-layer logistic regression, we can have multiple layers with some nonlinear activation functions in there in order to increase the representational power of the architecture that we're using for this problem here. So let's go ahead and let that train. Okay, so once our more powerful model is done, this is what the learning curves look like. So here, the difference is that at some point validation loss kind of stops improving and it starts getting worse here. So this is, kind of a classic view of the learning curve where overfitting is occurring, right? So this looks much better, right? And here you notice that, we're also overfitting, so we're able to drive our the actual metric that we care for to 100%, right? So that might not be achievable by a model that's doing well in generalizing, but that kind of shows that we're overfitting here as well. Okay. So, at this point, this is what you want. So now at this point, we've got a model that's sufficiently has a sufficient capacity to overfit. So now that leads us into the next section where we want to apply some mechanisms so that we fight that overfitting and find kind of the right balance. Of course, the first thing we've already talked about this before, we could just stop training when overfitting begins, but we'll look at some other methods in the next video for improving generalization. Okay, so to summarize what we were just talking about, so first of all, if your training doesn't seem to get started and your loss isn't going down, you've got something wrong with your parameters for the gradient descent for your optimizer. So try increasing or decreasing the learning rate, maybe look at some different optimizers. You can increase or decrease the batch size. So those are some of the things that you can do. If your model is fitting, the training loss goes down, but like your validation metrics don't generalize. So your validation metrics are stuck at like random guessing or no better than like a baseline. So that's kind of one of the most difficult problems you can face. It could just be that you don't have data that's sufficient. It doesn't have sufficient information to predict the targets with the data you have, right? So it might just be random noise in your data. It's possible. So if you do have data that's something like a image classification task or sequence data, the right kind of architecture might be able to solve it, right? So those will be some of the things we'll look at later on in this class. So finally, if your model fits and the validation metrics are beating the baseline, so it looks like it's doing something, but your validation loss never sees that typical where it goes up to indicate that you're now overfitting the data sufficiently. So you can start trying to regularize your model. So if that's the case, you always need to have a model that can cross that line of overfitting, so you know where that line occurs, right? So, but this is usually a relatively easy problem to solve. So you can, for neural networks and deep learning, it's easy to solve. You can always increase the capacity of your model. You can add more layers, you can add more units to layers, some things like that. Okay, so that's it for this video. I hope that's useful, and then I hope you'll stick around with me for our next one, where we will talk about, once you have your model overfitting, how you regularize it in order to find the best balance between underfitting and overfitting.